We wrap up our chapter 25 discussion with something called dielectrics. So, what is a dielectric? Well, it turns out it's pretty much everything. But in particular, let's imagine that we've got a bunch of polar molecules. So, one side's positive, one side's negative. Okay, and they're like randomly distributed. So you have all these little dipoles sitting here all over the place, randomly distributed. So they all have little dipole fields that are going all over the place, but they're all random dipole fields. And so if you do the vector sum of all those fields, it's going to add up to be 0. Okay, so now if you apply an external electric field, all these little dipoles are going to torque in that field. And so what's going to happen is, in the presence of the external field here, so in the presence of an external electric field, all the dipoles are going to line up more or less along the field. And so all the individual dipole fields are going to add up, okay? And so as all the dipole fields add up, then what that's going to do is that's going to make their own field, okay? And that field is going to be in a possibly, I mean, that field when it lines up like that, okay, is going to be even stronger field in here, okay? So that it amplifies essentially the field. Okay. All right. Well, so what does that do if you were to put a dielectric into a capacitor? Okay. So you have a capacitor and you put a dielectric into the capacitor. So that means we have some charge Q, and minus Q here, so there's going to be an electric field in here, okay? And so what happens is, if you put a dielectric in here, then the effect of that is going to suddenly change things, okay? So that means that now the voltage is going to be different, because we know that the voltage is going to be related to the electric field in there. Now I have all that dielectric in there, so the same charge is going to end up having an induced electric field in here. So what's going to happen is you're going to end up with positive charges on one end, negative charges on the other end of the dielectric, and that's going to end up with an electric field now in that direction. And so the total electric field inside the dielectric is now going to be lessened. So the electric field is going to be inside the dielectric is going to be less than what it would be otherwise. Well, the voltage is E times D, so that means the voltage is now going to be less than it was otherwise. Well, capacitance is Q over V. So less of a voltage for the same charge means an increase in capacitance. So now the capacitance is going to be greater than it originally was. And so by sticking the dielectric in there, then what you've done is you've increased the capacitance. Well, from an engineering standpoint, one of the big problems with capacitors is to get a really big capacitor, then the plates need to be really close together. Remember, epsilon naught A over D. Okay, so if you wanted a very large capacitance, you would need to have a huge area and a small distance. Remember, epsilon is 10 to the minus 12th, something times 10 to the minus 12. So you need to have a huge area and a tiny distance in order to compensate for that. Well, the problem with that is that if these plates are really, really close together, the least little thing could bump it and make them touch, and it shorts out, and it's no longer a capacitor. And then all the stored energy is suddenly released. Well, that's not good. Okay, because if you release the energy suddenly, it can be released explosively. And I've seen capacitors that have failed, and they sometimes when they fail, they will fail explosively. So, from an engineering standpoint, you've got your two metal plates, and it would be useful to put something between them that will be an insulator. Well, it turns out that a lot of these things that are insulators tend to be very polar molecules, and so that means it's a dielectric. Well, that means you've increased the capacitance even more than you would have otherwise. So we describe a dielectric. We have something called dielectric constant. Symbol for dielectric constant here is kappa. That's not a K. It's a lowercase Greek kappa. And so the capacitance is increased by that amount, kappa epsilon naught A over D. Okay, that's it. That's what happens with a capacitor with a dielectric in it. Okay, so you've just simply increased the capacitance by that factor right there. And so that's really the main thing that you have to remember about the dielectric. Now, how do you know the dielectric constant? Well, you look it up. Okay, so you look it up on page 732 of your book. There is a list on the upper left of dielectric constants. And notice some of these things, dielectric constants real close to 1, so they don't really do much. But some things have dielectric constants in the hundreds, meaning that you put a little thin film of something between the two plates. It acts as an insulator, which lets you put the plates really, really close together. But you also end up not just getting the effect of putting it close together, but multiplying the capacitance by hundreds. And so that becomes a very important sort of thing. Now, the problem with a dielectric is that you've got these molecules, and if you put a big enough electric field on here, you can literally pull them apart. And at that point, you have now destroyed the dielectric. So we often talk about the dielectric strength. The dielectric strength is the maximum electric field that you can put across the dielectric before you rip it apart. Okay. Now, when I started this discussion of dielectrics, I said, dielectrics are anything. So you think, well, what about a hydrogen atom? Got a proton in the middle, you got an electron here. If you apply an electric field, what happens is the proton actually spends a little bit more time to one side, the electron a little bit more to the other side, and so even a neutral hydrogen atom will become slightly dielectric in the presence of an electric field. Now, obviously, certain things like sodium chloride become massively, are already dielectric. And so there's other sort of things that are very dielectric to begin with. They're very polar molecules to begin with. But even neutral things, if it's made of protons and electrons, if you apply an electric field, then the electrons are going to be more on one side, the protons more on the other side. It will have a little bit of a dipole moment and therefore be a dielectric. So pretty much everything in the universe, if it's made of protons and electrons, and that's pretty much all matter, other than the neutral things like neutrons, then that is going to be a dielectric.